Hello, everyone. In this lesson, we will learn about the tool coordinates and user coordinates of robots together. In the previous lessons, we have learned about the hardware system of industrial robots and simple debugging, gaining a basic understanding of the world coordinate system and the joint coordinate system, and enabling the industrial robot to perform simple movements. However, if we want the industrial robot to perform more complex movements or tasks, controlling it only with the world coordinate system and joint coordinate system would be quite difficult. Therefore, in this lesson, we will deeply study and explore the tool coordinate system and user coordinate system of industrial robots. This will allow us to control the robot more effectively for complex operations. Next, we will study three main contents: objects of study and reference objects, the function of the tool coordinate system, and the function of the user coordinate system. Through this lesson, I hope everyone can accurately describe the definitions, functions, and principles of change of the tool coordinate system and user coordinate system compared to the default coordinate system, and be able to use the tool coordinate system and user coordinate system for programming and debugging industrial robots. First, let's learn the first part, objects of study and reference objects. In kinematics, when studying the motion process of objects, it is necessary to select reference objects and objects of study. Now, please think about a question. What does a robot do in actual applications? What would be the following reference objects and objects of study? This is a FANUC industrial robot performing arc welding. This is a FANUC industrial robot performing spot welding. This is a FANUC industrial robot performing handling tasks. From the different application fields of robots, most robots hold tools, welding guns, grippers, etc., to process workpieces at fixed points on the workbench. We habitually take stationary objects as reference objects and moving objects as objects of study. Therefore, here we take the tool as the object of study and the workbench as the reference object. The robot essentially establishes a relationship between the tool and the workbench, which is also called a position point. To express the relationship between the tool and the workbench, the robot introduces tool coordinate systems and user coordinate systems. Next, let's look at the second part, the function of the tool coordinate system. 1. Default tool coordinate system. We define the center of the flange as the origin of the tool coordinate system, with the direction towards the flange positioning hole as the plus X direction, and perpendicular to the flange outward as the plus Z direction. Finally, according to the right-hand rule, the Y direction is determined. New tool coordinate systems are derived from changes relative to the default tool coordinate system. 2. TCP. Tool center point, that is, the tool center point. The so-called robot trajectory and speed generally refer to the trajectory and speed of the TCP. The TCP is usually set at the center of the gripper, the end of the welding wire, the front end of the spot welding arm, etc. From the objects of study and reference objects, we already know that the tool coordinate system is an object of study in motion, but what role does it play in actual debugging? We understand how the industrial robot's gripper posture and position are obtained through these two figures. From these two figures, we can see that if adjustments to posture and position are made only through the joint coordinate system or world coordinate system, multiple moves are necessary to complete the adjustments. If we establish a tool coordinate system in advance, when completing the workpiece gripping, determining TCP, i.e., the tool center point, can facilitate adjusting the tool's posture. Determining the tool's feed direction can facilitate adjusting the tool's position. Characteristics of the tool coordinate system. New tool coordinate systems are derived from changes relative to the default tool coordinate system. The position and direction of the new tool coordinate system maintain an absolute position and posture relationship with the flange but keep changing in space. In Figure 1, the tool center point moves 31.68 mm along the Z direction from the flange center, with no changes in the X, Y, or Z directions. In Figure 2, the tool center point moves 78.82 mm along the Z direction from the flange center and 15.71 mm in the negative X direction. Its posture changes with the angle of the tool center point. Next, let's look at the third part, the function of the user coordinate system. Default user coordinate system. The default user coordinate system user 0 coincides with the world coordinate system. Me user coordinate systems are derived from changes based on the default user coordinate system. From the objects of study and reference objects, we already know that the user coordinate system is a reference object in motion, but what role does it play in actual debugging? On a non-inclined workbench with 5 workpieces, how should the robot complete the point adjustments of each workpiece most quickly? From the figure, we can see that using either the default user coordinate system user 0 or the world coordinate system can smoothly complete point adjustments. From the figure, we can see that using the default user coordinate system user 0 or the world coordinate system would make it difficult to adjust each workpiece's position. However, if the coordinate system's 2 directions happen to be parallel to the workbench surface, it would be much more convenient. Therefore, we can understand the functions of the user coordinate system as 1. Determining the reference coordinate system. 2. Determining the movement direction on the workbench to facilitate debugging. Lastly, let's understand the characteristics of the user coordinate system. Me user coordinate systems are derived from changes based on the default user coordinate system user 0. The position and posture of the new user coordinate system remain unchanged relative to the space. In this lesson, we deeply studied the tool coordinate system and user coordinate system of industrial robots, understanding their functions, characteristics, and applications in actual debugging. By mastering this knowledge, we can more effectively control industrial robots for complex operations, improving movement accuracy and debugging efficiency. Finally, please think about this lesson and complete the following exercises to consolidate the knowledge points learned today and further deepen your understanding. This concludes today's lesson. See you in the next time.